So today we're going to have a look at the Earth's atmosphere and global warming by having a look at how Venus and Earth are similar and how they're not similar. We're going to talk about how the greenhouse effect works, and then we're going to see if we can try and save Earth from the Earthlings. So Venus is often known as Earth's twin for a variety of reasons. They are pretty similar. They both have quite a similar diameter. Venus's diameter is 12,104 kilometers, so 12,104,000 meters. And the Earth's diameter is 12,742 kilometers, 12,742,000 meters. So that's pretty close. There's only a 5% difference between the two of them. Venus is a little bit smaller, but only really by quite a small amount. In many ways, though, Venus and the Earth are pretty different. Here's some pie charts showing the gases in each of their atmospheres. We've got blue for nitrogen on the pie charts. We've got green for oxygen, yellow for argon, which is one of the noble gases, red for CO2, and then we have some trace gases as well, which I've just put down as other. If we look at Venus, Venus's atmosphere is 96.5% CO2. I mean, that's almost all CO2, almost all carbon dioxide. Earth's atmosphere, pretty much mainly nitrogen, actually. 78% nitrogen and about 21% oxygen. There is also some argon in there, nearly 1% argon, and just a tiny little sliver that accounts for the carbon dioxide. We're about 400 parts per million, 0.04% carbon dioxide in our atmosphere at the moment. And then there's some other bits and pieces as well, like helium and krypton and methane, some other stuff like that. 0.04% carbon dioxide for the Earth, 96.5% for Venus. Now, the average temperatures on Venus and Earth are also pretty markedly different. The average temperature on Earth is about 15 degrees Celsius. That takes into account winter and summer. It takes into account the poles, the equator. Take all those temperatures over the course of the year, average them out, and you end up with about 15 degrees Celsius. Venus, though, 450 degrees Celsius hotter. So the average temperature on Venus is about 465 degrees Celsius, which is insanely hot. In fact, it's easily hot enough to melt lead. Lead will melt at 327.5 degrees Celsius, so lead would very easily melt on the surface of Venus. Venus is closer to the Sun, and that does account for some of the extra heat that we see there. Mercury is even closer to the Sun, and it is not as hot as Venus. Now, the average temperature on Mercury is 167 degrees Celsius. It does get up quite a bit hotter than that. It gets up to a maximum of about 427 degrees Celsius. But on average, so taking into account nighttime, daytime, all the rest of it, 167. So if Mercury is closer to the Sun than Venus is, but Venus is hotter, what is it that's making Venus so hot? 4.5 billion years ago or so, the solar system formed, and with it, the planets formed as well. And in the early solar system, when the planets had just formed, Venus and Earth were pretty much identical, very similar in size, similar kinds of orbits around the Sun, and they were pretty much the same. Both of them probably had liquid water on their surfaces. Probably came from comets from the outer solar system. But Venus developed a runaway greenhouse effect. This meant that it then lost any water that it might have had in the first place. So we need now to work out what is the greenhouse effect. What was it that caused Venus to lose all of its water? What was it that caused all the water to boil off from Venus and to disappear out into space? Let's have a look at this. We've got the Earth here. And the Earth has an atmosphere. That means it has gas that surrounds the outside of the Earth. The Sun heats up the Earth. It sends out energy, and this energy comes in and it strikes the Earth's surface and gets absorbed. Some of that energy, after it's been absorbed by the Earth's surface, gets re-radiated back out into space. But some of it gets trapped. Some of it gets trapped in our atmosphere. There's carbon dioxide in our atmosphere, and what that does, it actually absorbs some of that radiation that's being re-emitted from the Earth, And it absorbs it and it makes the carbon dioxide molecules start to vibrate more, gives them more kinetic energy, which means that they get a higher temperature. When they vibrate more, they then emit more thermal energy as well, in the form of long wavelength infrared. So some of the sun's energy is being trapped. It's being trapped in our atmosphere, making the Earth warm up even more. Now the problem is, as we put more and more carbon dioxide into the atmosphere, there's more and more carbon dioxide to absorb that extra thermal energy that's being re-emitted from the Earth. So the more and more carbon dioxide we have in our atmosphere, it's like adding a thicker and thicker blanket to the Earth. The Earth's going to get warmer and warmer. Currently, as we've seen before, the Earth's atmosphere is about 0.04% carbon dioxide. That means 400 parts per million is what we call that. Now this graph down here doesn't use percentages, it uses parts per million. So 0.04 is about 400 parts per million. 275 would be 0.0275, for instance. So that's how this graph works. Now, Venus, we've said before, is 96.5% its atmosphere of carbon dioxide. Keeping that in mind, what do you reckon this graph shows us? The bottom axis, the x-axis there, is the year. Well, what this is showing us is that since the year 1000, so about when the Battle of Hastings happened, we've had somewhere in the region of 0.0275% carbon dioxide, 275 parts per million. And that carried on for hundreds of years from then all the way up there. I mean, it went up and down a little bit, but generally speaking was around then. And then in the 1800s, it starts to move upwards. Now in the 1800s, something happened to the Earth. Something happened to human civilization. We started the Industrial Revolution. We started burning an awful lot of coal. Coal contains carbon. And when you burn it, when you burn anything, you combine it with oxygen. So carbon combined with oxygen creates carbon dioxide. So when they burnt all that coal in the Industrial Revolution, they started to emit more and more CO2 into the atmosphere. And this started to increase the amount of CO2, carbon dioxide, in our atmosphere. As the world became more and more developed, we started burning oil and gas and having massive amounts of industry and so on. That started to go up and up and up. So in the 1900s, so from here, it started to move up. At the beginning of the 1900s, we had about 300 parts per million, so 0.03%-ish. But over the course of the next 100 years, so from 1900, the end of Queen Victoria's reign, up until about now, we've gone up an awful lot. And you can see this is not what the previous pattern used to look like. It used to sort of bobble along around 275 parts per million. But since we've started burning all of this coal and all this oil and all of this gas and pumping more CO2 into the atmosphere, shock horror, we've started seeing the levels of CO2 in the atmosphere are increasing. So this is the same graph, but now I've added something else to this graph. So we've still got the pink line, which shows us the levels of CO2. But also on this graph now, I've got the temperature records, again, since about the Battle of Hastings. Now, you're probably thinking, well, how could they have these temperature records? Surely they didn't have decent thermometers back then. But by looking at ice cores in Antarctica and using other archaeological methods, we can work out what the temperatures were back then. So we've got on our y-axis over here, we've got still the CO2 parts per million, carbon dioxide parts per million. And remember, we're looking at the pink line when we're looking at this one here. But over here on the right-hand side, we've got another y-axis. So it's a slightly odd graph. We're superimposing two graphs on top of each other. And this one shows how the temperature goes above the average. So the average is along here, this 0 line. That's the average, and was taken at about 1950, so just there. What you can see is that the temperature, again, bobbled along. It went down a bit in the 1500s and the 1600s. But really, when we've been starting to get a lot of temperature records, which is in the past 100 years or so, we're seeing that the temperature is rising up and up and up. Now, what can we deduce from this graph? What can we say by having a look at this graph? Well, the obvious thing to say is that as the amount of carbon dioxide goes up, the temperature seems to go up as well. So the more carbon dioxide we have in our atmosphere, the higher the temperature seems to be. Now with Venus, there's an awful lot of carbon dioxide in its atmosphere. It's 96.5% carbon dioxide, and it has an incredibly high temperature, 465 degrees Celsius on average. Our atmosphere, only 0.04%, but it used to be lower. It used to be down to about 0.03%. As we've added just 0.01%, just 100 parts per million, to our atmosphere, our temperature has risen by an entire degree. Now, what might happen if we were to add another 0.01%, another 100 parts per million? What might happen then? Probably the temperature's going to carry on rising up and up and up. We should probably stop this from happening because we're going to be ending up with all sorts of things happening to our climate. Freak weather events, massive storms, droughts, floods, the ice caps melting, loss of habitat for animals, polar bears are going to go hungry, all the rest of it. We need to slow this down. This is pretty interesting. This shows us over the last 150 years or so how the temperature has changed. So the number you got down at the bottom is how different the temperature is versus the average temperature, or the temperature taken in about 1950. Now in 2018, the temperature was almost an entire degree Celsius above the average. In the early 1900s, the early 20th century, it was a bit high because we still had quite a lot of stuff burning, but it's really in the past 20 years that we've really started to see this going up and up and up. It seems to almost be getting faster. So we need to save Earth from the Earthlings. We need to come up with a plan to save the Earth. And this is something that you need to think about. We don't want our planet to turn into Venus. We don't want that to happen. So how are we going to reduce levels of carbon dioxide? What can you do personally? What can you do to try and help? What can your family do? What can your school do to try and help with this? What do you think the government and companies should be doing to try and help? We don't want our planet to become Venus. Let's see if we can save Earth from the Earthling.